Okay, so the second half of 7.1. So far we learned what a system is. We learned how to look at a system solving by graphing. We learned how to solve a system using the addition method. And then what was the other thing that we learned how to do? Substitution method. Good. Okay, great. Now we focus on, well, what happens when a system is either what's known as inconsistent or if a system has infinitely many solutions. I think you already kind of have an idea about the graphs of these, but how does the algebra support the graphs? What would a graph look like if the system had no solutions? What would the graph look like of a linear system?
Vertical.
No, not vertical.
Parallel.
Tube. Yeah, exactly. Parallel lines. Absolutely, they'd be parallel lines. So let's talk about a system. First box, a system with no solution. No solution. All right, and this is the one that we're going to graph and see. So let's talk about this system first of all. Let's do 4x plus 6y is worth 12, and then let's do a 6x plus 9y is also worth 12. Okay, so here we go. Let's just use Desmos. I guess it's a little bit faster for us. Okay, so let's go to Desmos. There we go. Oh, yeah, hit that light for me again. Thanks, buddy. All right. All right, so here we go. Let's plug these in. So I had 4x and then plus 6y, and that was worth 12. And then the other one that we had was 6x plus 9y, and that was also worth 12. Okay, so taking a look at this picture, if I put this in projector mode, a little easier for us to see. Okay, taking a look at this picture, what do we see? What do we notice here?
They're parallel.
Yeah, we've got two lines that are parallel, right? And it's a system. So if I've got two lines that are parallel, then therefore they're never going to intersect, right? So I can't find, one single point that would satisfy both of the equation at the same time. So this is what the graph looks like for an inconsistent system. Does that make sense so far? Okay, so let's see how this is supported by the algebra then. So if we go over to the algebra and we do it. So let's go ahead and solve this by addition method. So I'm going to multiply this part. Watch what happens here. If I multiply the top by a 3, and I multiply the bottom by -2, watch what happens when I do this, okay? And it doesn't matter what you do because you're eventually going to get to this point, but this point gets us there faster, okay? So 3 4x's, how much would that be? Yeah, 12x, very good, okay. 3 times 6y, how much is that? 18y, good. And then 3 times 12? 36, right? Good. And then on the bottom one, 6x times -2? Negative 12x. 9y times -2? Negative 18y. And a 12 times -2? Negative 24. Okay. If I add vertically, we can kind of already see what happens. 12x and negative 12x, that cancels, right? Or sums to nothing. 18y and negative 18y also sums to nothing. And I get 36 minus 24 is 12. So look, I get 0 is equal to 12. On what day is 0 equal to 12? No day. That is never true, okay? So if you get a false statement, so this implies a false statement. Is everyone okay with that part? Everyone, that's false, right? Well, that would imply an inconsistent system. Okay? And you're going to see the answers in the back of the book are going to be this empty set notation or 0 with a line through it. So what we say is we say that the system is inconsistent. That's the way that we say a system has no solution. We just call it inconsistent. That's the word that we use. Okay, solve this system using the addition method if you can, and see what you come up with, okay? Do that right now for me, please. Annie, what'd you do first? Tell me what you did.
I multiplied the top by 2.
She says she multiplied the top by 2. Did anybody do the same thing that Annie did? Hands up if you did the same thing. I got 1, 2, 3. Most people did the same thing. Did anybody do anything different than multiplying the top by 2?
You can divide the bottom by 2.
Or you divide the bottom by, multiply by half on the second one? That's always well too. Okay. So if you do this, you get, what'd you come up with, Annie?
10x
Mm-hmm.
minus 4y
Yep.
equals 8.
10x minus 4y equals 8. Good. And if I rewrite the second equation here, and we add vertically using the addition method, what do we come up with here? We get, well, that cancels, right? And then that cancels, and then that's equal to what, 15? So 0 equals 15, never true. So what does that imply, you guys?
Inconsistent.
Inconsistent system. Absolutely perfect. Inconsistent system. All right, let's take a look at an example of an infinite amount of solutions. So let's get a picture of this graph. Let's see what it looks like as a graph. So I'll go over to Desmos and we'll get a picture of this. So can you guys help me out? What was the first one there?
Y equals 3x minus 2.
Y equals, I got a 3x and then a minus 2. All right, so I got this nice green graph over here. No big deal. Let me zoom out a little bit. Not a big deal. And then what was the other one that we had?
15x minus 5y equals 10.
15x minus 5y is worth 10. Okay, so check this out. I definitely have two equations here, but if I look at the graph, it looks like I only have one line. Why? They represent the same line. So there's obviously more than one way to represent a line, right? One could be a scalar of the other one, but in terms of what it looks like on the graph, it looks like one is right on top of the other one, right? So if I take the purple one away, notice I only see the green, right? And then if I take the green one away, well, it kind of stays purple because purple's a darker color. But whatever, we get the point of this, right? So I have two equations, but I am represented by only one graph. That's what the picture looks like for a system that has an infinite amount of solutions. Okay, let's see what the algebra looks like to support that. If you had to take a guess, what do you think the algebra is going to look like?
0 equals 0.
0 equals 0. Everybody always says 0, because does it have to be 0 equals 0? No. Could it be 5 equals 5?
Yes.
What about 9 equals 9?
Yes.
What about negative 1 equals negative 1?
Yes.
So what is common between all those examples I just gave you?
The same exact.
They're all true or false?
True.
They're all true. See the difference between that and this one? This right here, this gave us what's known as a false statement. So we're going to assume then, in this one, we're going to get a true statement. Not just a 0 equals 0, but any true statement, okay? So how do you want to go about doing this one? Should we use addition or substitution? Substitution is a good way to go. How come? Yeah, because I already know how much y is worth. Y is worth how much? It's worth 3x minus 2. What do I do with that information? I plug it in where? Where the y is for the second equation. So I'm going to plug it in right there so you can kind of see what I did. All right. So I'll choose, we'll go brown. So I'm going to say 15x minus 5 times, how much is y worth? 3x minus 2. And that gives me a value of 10. So here we go. I'm going to get 15x. I'm going to use the distributive property. So that's going to be a negative 15x. And then a plus 10 is worth 10. So what do I have here?
0.
I get 10 is worth 10. Don't I? Because 15x minus 15x, doesn't this stuff just go away, right? Cancel out to 0. So I get 10 is worth 10. What do you think about that? That's a true statement, right? Okay, that's a true statement. So this implies true. So then that would imply that we have infinitely many solutions. Okay? So here we go. How do we represent the answer?
All real.
Yeah, okay. Every book does it a little bit different. This is how this book does it. How to represent the answer, okay? Every book does it a little bit differently, but this is what you're going to see when you check your work in the back, so I want to show you. It's a set. It's a solution set, right? Because there are infinitely many solutions, and remember, a solution to a system is a location. It's a point, right? It's not just one single number. It's a point. So how do we represent that in terms of infinitely many solutions? Well, you have two choices. You say it's every single point x comma y. That's what we said so far. Every single point x comma y such that, that's our bar, right? Such that y is worth a 3x minus 2. Now, that's pretty easy, right? Because after all, where did I get the 3x minus 2 from? I just got it from the first equation up there. You see it? What's the other way you think I could represent the answer? Or what's the other way you think I could do it?
The x comma y.
Good. The solution set, x comma y, such that
Such that 15x minus 5y equals 10.
minus 5y is worth 10. Exactly. So where did that one come from? Well, that one just came from the second equation in our system. You get a choice, okay? Either that one or that one. You don't need to write both of them down. But this is a nicer way of representing, well, it's any xy point that satisfies y equals 3x minus 2, or any xy point that satisfies 15x minus 5y is equal to 10. Okay, try this one. Let's pretend right now that you don't know that it's going to be infinite, or maybe it's going to be no solution or inconsistent system. So go ahead and solve that one and represent the answer appropriately. Okay, help me out. Who's got it? Who wants to talk about it? DJ, go for it, man. What'd you get?
So I got true.
You got true. Okay, so what did you do? How did you come up with true?
I substituted with the negative 3y in the top equation. I substituted the y with 3x minus 4.
So you took that value and plugged it right there?
Yeah.
Okay, so that's going to give us 9x minus 3 times 3x minus 4, and that's worth 12. Okay, then what?
And then I distributed the negative 3 into the equation right next to it.
Mm-hmm.
And basically the two nines cancel out each other, and you got 12 equals 12.
Yeah, so 12, what does that mean?
True.
That's true, so what does that imply?
That is infinite many solutions.
Infinite many solutions, very good. Okay, and how did you represent your answer?
I represent is that x comma y.
Yep.
Such that y equals 3x minus 4.
3x minus 4, and you know what? That's totally acceptable. You don't need to put both in there, all right? Just one of them is fine, okay? All right, so you don't need to write it all out, just as long as we understand what's being asked of us, okay? It says the sum of 3 times a first number and twice a second is 8. All right, so these are words. We're going to take these words, we're going to do some math with them. If the second number is subtracted from twice the first number, then the result is 3, and we are supposed to find the numbers, okay? Have you seen these types of problems before? Yeah, you have, right? Okay. So what's always the first step in trying to solve these problems? What do you do? Write the equation? What do you mean, write the equation? You're on the right track, but before you can write the equation, what should you do first?
Have two variables.
We need variables, right? We need variables. So let's define the variables, okay? So let's let x be the first number. The first number. So x is the first number. Got it. So what should the second number be? Y, okay, I'm good with that. So let y be the second number. Okay, no problem. So y is the second number. So now that I have this information down, how can I take what I have defined and let's work on this individual statement up here. The sum of 3 times the first number and twice the second is 8. How do I transform that into a mathematical statement from words?
3x
plus 2y.
Yeah, 3x plus 2y is worth 8. That says the sum, because the addition sign is between them, the sum of 3 times the first number, since x is the first number, we're going to do 3x, and 2y, y is the second number, is equal to 8. Perfect. I'm on board with that. Awesome. Okay, now I have this next statement here. If the second number is subtracted from twice the first number, the result is 3. How do I write this down?
2y minus y.
Very good. You guys said it right. 2x minus y is worth 3. Very good. That says right there, right? The second number, which is y, is subtracted from. So that means it is going to be first number minus that y, okay? And the first number happens to be just twice of it. So 2x minus y equals 3. Great. Awesome. Go for it. Let me know what you get. Okay, so many people said that they got the answer of 2 and 1, so I went ahead and graphed it to see quickly if we got it right. So we had 3x plus 2y equals 8 and 2x minus y equals 3, and I put the point in 2, 1, and it definitely crosses. The intersection of those two lines is 2, 1, so the solution to the system is 2 and 1.